Hey guys, this is a Coherent Novus 2000 medical argon ion laser. This is a 2.5 watt blue and green argon laser, normally used for ophthalmic like eye procedures. I found this at the scrapyard. It's pretty powerful as far as argon lasers go, 2.5 watts. And since the low efficiency of argon lasers, it takes a lot of power, as you can judge by the power cord, 6 gauge. Input rating is 230 volts at 45 amps. According to them, this is a Novus 2000, made in August 1993. We'll have to see if this thing actually works or not. Output is fiber coupled. It comes out on this fiber optic cable. This has some sort of a this either connects to another fiber or focuses into a beam. Because if you look down there, you can see there's a lens in there. This is the actual output fiber. Other than that, we have a bunch of things for these are labeled things for a slit light. I think this is used with a microscope to look in the eye to see what you're doing when you're doing a procedure. In front there's I was lucky enough to find the key. There were about 3 of these there at the scrapyard from Vancouver General Hospital, apparently, based on the asset tags. And this happened to have, one of the other ones happened to have a key, and it happens to match this. This one was the one in the best condition. A couple of the other ones had fiber delivery on the front, and this one has it on the back. And this one had the best fiber optic cable, although I'm somewhat doubtful that this fiber optic still works after all the treatment this thing got in the scrapyard. The laser is controlled by a foot pedal, so the doctors have their hands free, and apparently the doctors are so stupid they don't even remember what foot they have to use and have to be reminded. Cat inspection approved. Okay, let's make that not quite so horrendously dangerous. So, after untangling all the connections, the connections coming out of the laser are pretty simple. There's this for the foot switch. This switch is almost certainly an interlock for a room interlock, so like you could put a switch on your door so the laser won't run when the door is open, although almost no one ever seems to use that, so this is likely just a short. And this, I'm not sure what this is for, but it goes up to this, what appears to be an add-on box that takes power in and the connection from the laser, and has these 2 circular connectors that go out to this joined cable that goes over to this that's labeled microscope eye safety filter. So I'm not sure if this is an output for like a shutter, or puts an attenuator in front of the eyepiece when the laser is on or something like that, but hopefully there's no interlock, or if there is, we'll have to bypass it to get this thing to run. Okay, moment of truth. Here we go. Okay, probably off because the key switch is off. Let's see what that does. Oh, nice pump starting up sound. Display test. Bunch of valves clunking, it sounds like, or shutters perhaps. Okay. A warm-up, I'm assuming. Error 207, error 2. Yep, so something is not right with this. Can we turn it to ready? No, cannot change anything. Nope, I didn't figure these would work given that they were thrown out. Oh, E-stop actually completely cuts power. I've had to look online for a manual or service manual or anything about the error code, and I couldn't find anything. And a laser like this isn't really useful because a $50 tiny little diode laser about that big can produce about as much power as this can. So I think this will be cool just as a teardown. I'll see if I can perhaps hot wire it to try to get the laser tube running. Anyway, let's begin the teardown. Okay, it took me a few minutes to figure out how to open this. So we just stick a screwdriver in there, pop it open, and there we go. Oh, look at that. Oh, that's so cool. What do we have? Some big transformers. Danger, high voltage, that's always a good sign. Some water cooling stuff, reservoir and a pump, a big radiator and fan on the bottom. What's this thing? Some sort of terminal block? Oh no, it's fuses. Little fuse panel, a whole bunch of fuses in it. Haven't seen something like that before. It's cool. And the other side. There we go. Oh, here we go. Oh, look at that laser tube. Wow. Yep, that must be the Argon laser tube. We have this other thing next to it. I'm not sure what that is. And a good, nice old school board. What's that? Yep, 68,000. Classic processor. I'm assuming that's the filament transformer right there. What else? I can't really see behind there. Okay, let's continue pulling panels off. Let's try to get the top panel off. I really want to see how the optics on the end of this work, because I want to see how they're coupling this laser onto the fibers. You also got a little daughter board thing just sitting in the corner here for some reason. So they ran out of room, didn't have room to put it. No, there's nothing on that side. Yeah, I guess they must have just run out of room. Looking a bit more at this laser tube, around the outside there's you can see a coil of wire that's used to generate an axial magnetic field down the bore of the tube. I think that's to constrict the arc. And this thing off to the side seems to be connected down here to the gas fill port, so I'm thinking this is some sort of a gas reservoir. Not exactly sure why you need that, I guess due to expansion or something like that. Yeah, this is definitely the filament transformer. You can see the white wires from the filament running up to there. Oddly, there's a capacitor up here that's connected to the transformer. I wonder if they're doing some sort of resonant thing, because that's connected to the secondary and there's some shunts in there. Not sure what's going on there. Behind this board there's some other power supply. I think it might be driver or control for the main laser power supply. And down here is a really nice radiator. If you're looking at my Twitter, I'm working on a huge water-cooled LED setup, so I think this is actually just the ticket for cooling that. The serviceability on this thing is great. There's these little things in here that you give a push to. If I can get that. And then the front just sort of pops off, and you do the same on this one. It just pops open and opens up. And we are being mooned. Yeah, this is probably just display stuff, a few switches. There's a flat flex thing here, which I'm actually not sure what that's for, because this doesn't have any flex buttons or LEDs on flex or anything like that, so I'm curious as to what that actually is for, unless it's just ground, because they're very paranoid in medical systems about grounding. You can see these ground wires going everywhere. This panel has its own ground wire. Yeah. Okay, here comes this. Whoa, look at that. There's some huge capacitors. Let's see, what are these? 140,000 microfarad, 250 volts. All in parallel. And what else do we have? Some big bricks. There's some diodes. That's dual MOSFET, another dual MOSFET diode. Let's see, control board over here. Does that go off there? Yes. I don't think it's likely we're going to be able to easily hotwire this. Ooh, this back panel here is water cooled. You can see a pipe that runs down it, and then the lines run off there. And behind it there's more stuff. I see some fuses, some inductors. There's some sort of some sort of coil thing back there. And these things, which I thought were transformers earlier, are actually inductors, because it says on top of them 20 amps, what is it, 2 millihenries, no, 24 millihenry at 20 amps, or 6 millihenry at 40 amps, depending on how they're wired, I guess series or parallel. I've had a quick trace out of this, and I'm not quite sure what they're doing here, because 250 volts is not enough to handle rectified 240 volts mains input. So they're clearly not just rectifying the input and storing it in these caps, which is what I figured they would be doing. So I'm wondering if these inductors and these diodes are part of a LC converter on the input. I'll have to actually fully trace this thing out to figure out what they're doing. I'm quite interested in that. And inside this optical block, a whole bunch of optical switching stuff. Let's see what we got here. So, the output of the laser tube comes out of here. There's some, looks like rotary shutters of some, or filters of some sort. And the beam goes up here. Actually, no, that's the aiming beam laser. It's the small, I think it's a 2 milliwatt helium neon. That beam comes through here, through like I said, a shutter. This must be a beam combiner. I'm suspecting that mirror right in there will pass the helium neon but reflect the argon ion beam. Yeah, so that goes through here. There's another, yeah, these are little sort of like solenoids but rotary actuators. So that puts this, that looks like a beam dump actually. That would reflect the beam off into this thing for to dump it. And then we have some sort of other, that looks like it might be some sort of power meter. Another beam block, and then this is the thing that couples it into the fiber. That will be a really precisely made thing to couple the beam, to focus it down and couple it into a fiber, which is, I'm not sure the size, if it's a multi-mode, something like 100 or 200 micrometers. If it's single mode, it could be around a micrometer or so. A telltale sign that this is that are these two adjustment screws for XY, so you can move the lens slightly to align it perfectly with the fiber, the input fiber, input of the fiber. That doesn't look right. There's what looks like a burn mark or a melted through section on that filter. Looks like this will come off. It's just a standard, standard fiber connector, just like on the other side. This one had a couple of these wires. I wonder where those go. Let's see. Here's the end of this. So what's on the end of this thing? Get this off. So it's just a resistor, so the machine can identify based on what resistance value it measures what end piece is connected to it. I'm actually guessing that this circular thing is a polarizer that can just be rotated to change the polarization of the aiming beam laser. Not sure why you would want to do that. Maybe something to do with blocking it out or more easily seeing it when you're using the main laser. I've traced out the power stage of the power supply here, and everything starts to make a lot more sense. This basically consists of an LC filtered power supply that forms a tracking regulator to a linear power supply that directly drives the laser tube. There's a few other extra diodes in here for, I think, for starting and protection, but basically these four large MOSFETs, 50 amp, 500 volt, act as a linear power supply to control the current through the laser tube. And the gate drives all go off to a control board on the side, and these use these sense resistors to properly drive them to maintain equal current sharing. There's a little inductor and some other SCRs here that I think have to do something to do with generating a pulse to start the laser tube, although I'm not quite sure how those work. Yeah, so effectively this thing is a 5 or 7 or whatever kilowatt linear power supply. I'm assuming the laser tube takes something like 150 volts at around 30 amps. It could be more. The inductors on this are rated for up to 40. You don't often see linear power supplies running at this high power level, so to keep the dissipation in these pass transistors down, this input stage works as a variable tracking pre-regulator to minimize the voltage drop on these, so you can regulate the DC bus just a little bit above the voltage of the laser tube to keep the dissipation low. And this is called an LC filtered power supply. It's sort of like a buck converter. If you just cover this up, that section here looks exactly like a buck converter. So what it's basically doing is pulse width modulating the 120 hertz sine wave. Instead of like a buck converter normally runs at many kilohertz, this one runs at basically mains frequency. And I initially thought this was just a diode bridge here, but I missed that these are actually SCRs. And these are used to phase shift the rectified sine wave, and you just adjust the phase shift to adjust the average DC voltage across the inductor, and the inductor then filters out the current. So yeah, you'd move this edge to adjust your, with a feedback loop to adjust your voltage on the DC bus, and the current will stay relatively constant during the cycle because of these inductors here. And then the input current will look almost like a square wave due to that, rather than the very peaky current you would get from if you just had a rectifier. And that's also how you avoid having overvolting these capacitors. These are only rated 250 volts, where you have an input, 240 volt input, which has around a 330, 340 volt peak. And because of the inductors, that sort of becomes almost an average. So when the duty cycle is all the way up, you get just about something around 240 volts on the caps. I think the factor was 0.9 or 1 over 0.9 or something like that. So that's what the big control board was for generating all of these pulses, maintaining the current control, maintaining these tracking pre-regulators. So I was hoping I could just sort of hotwire this to run these MOSFETs to drive the laser tube, but that won't be very easy because you'd have to get the whole pre-regulator working. So in the actual power stage, this diode bridge and this diode are these parts. Obviously these inductors are the big inductors we saw on the bottom. The 4 MOSFETs are these modules you see here. You can definitely tell they're in linear mode because the wiring you see going to them, there's no care taken to keep the inductance low. In fact, the ground wires that normally go with the gates aren't even used. They're just taking the return current path through these resistors. And then these other circuits, this diode is this one, and these 2 parts, the one on the left is this one, the one on the right is this one. Yeah, I'm not quite sure how this works, but it's got to be something to do with generating the pulse to initially ignite the laser tube. This diode here acts as a catch diode so that when both these SCRs are off, and the inductors continue to want to drive current through, that can come from somewhere. Otherwise the voltage would go negative and you might damage the SCRs. I think the reason they're using this linear power supply design rather than a switching supply is this has to be able to produce precise narrow pulse widths. And with a linear supply or with a switching supply, you'd have to wait, for example, the current in an inductor to ramp up or down, and they don't want that here. Don't you just love it when things are actually designed for service? This thing is beautifully mounted on these little sort of universal joint things, so the board just flips out for service. Oh, it's so beautiful. Here's a much better view of this now that the covers are off. Yeah, not much left in it now. Yeah, the laser's mounted on this massive aluminum U-shaped piece, and there's this, it mounts over here with a nice machine piece. There's a lot of power supplies in this thing. There's this, seems main linear supply. What does this have? +5, -5, and out, whatever out is. This is the filament transformer. It looks like there's several taps to connect the filament to different voltages, and this is the output from the negative output from the driver. Curiously, there's also a capacitor here that looks to be connected across another winding that's in the same winding group as the main filament winding, so they're doing some sort of resonant thing. And then the primary coil is here, and there's some shunts. So yeah, they're doing some sort of a resonant thing to get some sort of resonant rise on the filament. I'm not sure exactly why they're doing that. Here is the actual filament connections into the tube. See the nice insulators there. I think that's the laser beam goes down there across this little bellows. And the bottom, I think on the bottom here is the adjustable high reflectance mirror, and that probably is you can trim the angle of that to get the beam going straight down the resonator cavity. Yeah, there's this very large coil around the tube. Judging by the wire size, about an amp or so. Well, it's hard to judge because this is connected to the water-cooled section, so you could actually put quite a bit of heat into this and not have it overheat. And then I'm not sure how the upper mirror is adjusted, or if that's even integrated into this top section. I'm curious about that. Yeah, and I figured this thing must be some sort of a gas reservoir, because it definitely does connect over down there into the tube. And there's some sort of a sealing pip with a bunch of you see those are soldered or brazed in there. This has a 35 volt cap on it, so I'm assuming out is 24 volts. Actually, these are plus sense and minus sense, and the output, according to the supply, is 12 volts at 6.8 amps. I think that's a keeper, a nice 12 volt linear power supply. On the back panel, there's just the main input circuit breaker, another power supply. Let's see what voltage that is. No, and another thing labeled Coherent Medical that seems to be another power supply. I'm curious as to why they had to design their own power supply for this. Maybe it was some sort of safety reasons. And what else? Another transformer, signal transformer, and then just a bunch of stuff for the I/O panel, and of course this little fuse thing. This little board that was mounted off in the corner seems to be some sort of a fan controller, because this connects off to the fan, to what's probably mains input, and to a thermistor, which seems to be under this radiator right there. Thing is, the fan came on immediately when I turned this on, so I wonder if this is like just running at a low speed. When the airflow gets hotter, it speeds it up, because this looks sort of like a triac with a light dimmer circuit. So right, yeah, right there it says smart fan. There's also a bunch of jumpers here, or a jumper link here that has 60 60 cycles, I guess. I wonder how often these laser tubes blow, because they make it oddly convenient to disconnect the water. The main board has a typical embedded system from back in the day when this thing was made in around 93. Has a 68,000 CPU. Looks like it's running at about 8 megahertz, judging by that oscillator. A few other support chips. There's some parallel I/O timer chips. I think these have 3 timers and some parallel I/O in them. Some battery-backed SRAM with built-in batteries. I don't like those because you can't replace the battery inside them. You have to replace the whole thing and you lose the data. Well, I suppose if the battery's dead, you've already lost the data. There's some 12-bit ADC, a couple of 12-bit DACs, lots of glue logic. Over here there's a 16-channel JFET-based analog mux. Other than that, there's just a few power supply-like things. I think these... That's... yeah. 2N08, that's a MOSFET. There's another one over there. Yeah, so some sort of power driver on this. Wonder if these resistors have something to do with that. And a cap. Was this a super cap? No, that's just a 50 volt 1000 mic. Oh, this connector over here, not been soldered very well. Nope. Couple of bodge wires on this, but not too many. Pretty clean layout. Typical vertical routing on this side and horizontal routing on the other side. Here's the control panel board. Not too much on this, just a bunch of these large flat field LEDs to light the these indicators. It's probably a micro there, P8032. I'm not sure about that though. EEPROM, some really nice encoders. Other than that, not too much. I was curious as to what this flex was for. It goes off to the front, and I didn't think there was any onboard lighting, but it turns out that connects up to here, right next to this, which is labeled output 64 volts AC 1.2 kilohertz. So that's got to be an electroluminescent display panel or light in the back. It's probably to light up these the text around these controls so you can see it in the dark. These two boards seem to connect with these two D-sub connectors, which I found odd given that everything else is done over just these normal regular internal connectors. I'm not sure why they chose to do those via D-sub. Here's the board from the power supply. This board is labeled the SCR power supply assembly. This has lots of analog stuff on it. Clearly an isolation barrier here. This is the mains connected side. This is the low voltage side. You can see from this other board, this is the board that was on the power module. This has the 4 resistors that we saw in the schematic there. Yeah, these are 25 milliohm each. And these are nice 4-terminal sense resistors, so we have the groups of traces running off onto the cable. This also seems to have just some high-potted. What are these? Judging by the 1 millihenry and the high-potted text on here, I think these are coupled inductors. These are probably used to drive the gates of the SCRs. Yeah, those. Anyway, we have the sense resistor tracks going off to this. Those clearly come in here and go off to a whole bunch of amplifiers. It looks like all the tracks are on this side. Yeah, these hook up to a bunch of amplifiers. These must perform regulation to drive the main MOSFET gates. On this side, I think this is the driver for the coil that's on the laser tube. This probably is just a basically a buck converter, but using the laser tube coil itself as the inductor. So sort of like how a DC motor driver works. So that would be the FET. This is probably, that's a transistor. This is probably going to be it's probably one of these. This is probably the freewheel diode for that. Yeah, so I was wondering where that driver is, so it's on this board. Other various analog sensing, probably high voltage sensing for various voltages in the power supply. Bunch of analog, some digital stuff. A whole bunch of optos here, and this curious component in an odd package. This is an ISO 120 capacitive analog isolator. This basically converts an analog signal to pulse width modulated digital, passes it across an isolation boundary using capacitors built right into the ceramic substrate of this package, and then it filters it back into an analog value. And apparently this has a pretty good bandwidth of around 60 kilohertz or so. There's a few LEDs on this. This one's labeled magnet. This one's labeled shutdown. This one B plus greater than 10 volts. Something else. This switch is between current and light. I wonder if that's switching between regulating the laser tube current or the actual light outputs. And there's a really, really nice feeling pot here. Probably some sort of current control. Other than that, there's a few analog muxes or analog switches. Yeah, not too much else on this board. Here's this transformer assembly from the back panel. It only has 2 connections, mains input and some sort of output. It seems to be some sort of a speed controller. There's a triac here, and it seems to control. Yeah, it seems to do phase control of something, perhaps a heater or a lighting controller or something. I know this connects to the whole thing connects to a microscope. This may be something to control a light or something on the microscope itself. Here's this other board. This was mounted on the bottom corner of one of the doors. I really have no idea what this does. This connects up to these 2 ribbon cables and a few others, and just on this wiring harness, that board connected there, and then this seems to just go over to the main board to this one. So I really am not sure what this does. It has a IRF640 MOSFET on it, and a bunch of mostly, almost entirely digital logic, a few analog devices parts. Those are just op amps, so this seems to be some sort of analog processing or amplifier board. This also has just an empty footprint, as I've seen on another thing, on one of those old, the Kodak Ectopro high-speed camera. This is a package that's just wired into only power. It's likely there so you can do bodges, probably for something during development. If they wanted to bodge something in, they would have a place they could put an IC to conveniently do that. And the last board on this is this what was in this box that was mounted onto the back of the unit. It just seems to be a power supply, a few transistors or something. I think this is just some sort of a lighting or power supply for some equipment like a microscope that was connected to this, because yeah, not many of these pins are used. I wish we could see this optical stage with the full argon laser beam going, but the aiming beam here is going to have to do. I initially tried powering this up with the power supply included or on it, but that seems to be dead. It was drawing only about 100 milliamps. So I've hooked up an external laser supply, got a ballast resistor in here, because this is 1600 volts, this is 1250 or something like that. Yeah, the aiming beam is working. What I was thinking is a polarizer here. It is a polarizer, but it's not to change the polarization. That's actually the aiming beam intensity control. As you turn that, you can see on the tape roll the beam intensity changes. And it does seem that this junkyard fiber does seem to work just fine. I'm puzzled as to how this burn mark got in here, because no matter how hard you drive a small helium neon tube like this, it's not going to produce anywhere near enough power to burn a hole like that. The argon beam should not be able to come back this way, because this mirror reflects it out that way. I don't see anything here that can really reflect the beam, so I can only imagine that someone put a whole bunch of light the wrong way down this fiber, perhaps connected it to another laser or something mistakenly, and that burned this, although I would have expected if it was an argon laser, the beam should have gone down off that mirror into the laser, so someone, I'm not sure how they did this. Anyway, this thing is a beam or a filter. This will absorb the, when it's in the up position, it absorbs the blue spectrum. It says here, all down, green up. So when it's in up, it reflects the blue light off into this black beam dump. You can actually see the sort of, if I can get it to focus, the bleached portion where the beam was hitting. It wasn't quite, it was actually missing and going off and hitting something else, maybe hitting something on the PCB there. There's a power measurement in here. Let me see if I can show you those. If you look down in there, you can see sort of these like bare die photodiodes. It looks like literally they just solder wires straight onto the die. There we go. That should be a slightly more in focus image now. Yeah, odd style of photodiode. And if you look down in here, if I turn the aiming beam back on, you can see just about see the aiming beam hitting the photodiode. I'm curious as to why there's two, because as far as I understand it, the aiming beam and the argon beam have to be exactly in parallel so that they will go through this lens and enter the fiber properly. But I'm not sure why there's a second photodiode there. Perhaps something to do with the reflections, a second order reflection, or a reflection off the second surface of this mirror. This thing, you can see how this is the thing that couples the beam into the fiber, which is basically just a lens right there that focuses the light down to the exact point of entry of the fiber. So I pull this off, you should be able to see the beam die out. Yeah, just a thin, it's probably 100 or 200 micron fiber there. A couple of electrical contacts for the probe to detect what's on the end. And if I turn this, you should be able to see the beam intensity change. This is how this moves the lens in the X direction, so you'd sort of set that for the maximum value. And this is in Y, so if you throw those two off, you'd have to set that one for maximum, then you'd set that one for maximum. And there's also a Z-axis control. That one seems to be locked though. That just controls how the sort of spot size as it enters the fiber, and that's, I assume, has been preset. Really nice simple method of setting the mirror angle just with some set screws, so you can tighten them up, and there's a really small piece of aluminum connecting these two sections. This produces some interesting interference patterns when you move the fiber. If I move the fiber here, this is near the exit end, you can see sort of the pattern changes more in the center than at the edges. This is just a very slight, like a few degrees movement, bending of the fiber. If I bend it near the entry end, it changes much more evenly, so somehow like it disperses, the pattern sort of disperses as it goes through the fiber. I'm curious as to what this fan control circuit does, so I've got this hooked up. The fan's running at sort of a nice slow speed. Let's try putting the thermistor into some hot water. Oh yeah, sped up a little bit, not a huge amount though. It's a pity we weren't able to see this laser tube running. I really would like to try to get it running. If anyone has any info on this, that would be great. I basically need to know what the tube voltage is, what the tube current is, how much current to put down this electromagnet here, if the filament needs to be continuously energized or if it needs to be de-energized when the tube current is flowing. Because I've seen some magnetrons where you actually have to turn off the filament when the main tube current flows, because the electrons produce their own heat and heat the filament up. Yeah, if anyone has any info on this tube, it's model number Coherent, model number Novus. That's probably custom assembly for this laser, but the tube seems to have a standard model number. Yeah, so if anyone can get me any information on this, or a spec sheet or anything so I can try to get this running, I'd be grateful. And if anyone wants this tube, let me know. I can probably send it to you if you pay shipping plus a modest handling fee, because if you actually want it to survive, I'm going to have to build some sort of a crate around it for it to have any chance of surviving shipping. Anyway, I think that concludes this teardown. A lot of cool stuff out of this. Lots of scrap metal. Probably get back the $50 I paid for it just in the scrap. Nice base. I don't know if I'm going to keep this or scrap it. It's so going to build a cart or something with it. That water cooling thing is going into the 5 kilowatt LED setup I'm doing for the garage. If you've been paying attention to my Twitter, water pump might be able to use that too. Don't have any use for these huge inductors. Those will probably just end up being scrapped. Yeah, and a whole bin over here of goodies to keep. Anyway, hope you found that teardown of the Coherent Novus laser interesting. Thanks for watching.